Okay, so in this video, uh, we will study about magnetic properties of matter. In the last video, I said that we will be able to complete this portion, but we could not. And now we will do this. This is actually the last video because after this, there's no more stuff. In this portion, they just magnetic properties of material, about the three types of material, how they conduct, why do they conduct, why do they have magnetic field, why do they act as magnets, and why don't they, and then this permanent and non-permanent magnets here. This will probably take like 20 minutes, I think, not much. This is actually the last video, not the last one. This one is the last video. So we will start with magnetic properties of matter, of materials. Okay, so to start with, first we should know that according to their according to their magnetic properties, according to magnetic properties, materials are divided into three: diamagnetic, paramagnetic, and ferromagnetic. Okay, out of this is the least magnetic, this is the highest magnetic, this is the least magnetic, this is the highest magnet, this is like moderate. Okay, so now what makes diamagnetic the least, what does make ferromagnetic the most, and paramagnetic the medium one? Okay, so in the last video I taught you about magnetization and magnetic intensity. It has all to do with this one page has all to do with magnetic properties of material. So I did take like 25 minutes last video of this one, and just see that because it's all related to that. So in that video I talked about this constant x. Okay, like we'll call it as x. Okay, this constant x, what is this constant x? This is the constant, this is the material of the magnet, or it is called magnetic susceptibility. So what is magnetic susceptibility? It tells us how an object conducts magnetic field. Okay, it's all related to the magnetic properties of that material. Okay, this magnetic susceptibility, this is this constant over here. Okay, so according to this concept, in terms of susceptibility, x, material is diamagnetic if the x is negative. If the x is negative, or this magnetic susceptibility is negative, it is diamagnetic. If it is para, then it is positive but small, and if it is ferro, it is large and positive. Okay, that's the difference. They can say according to the difference of magnetic susceptibility, classify them. So they are classified on this basis. If it's negative, then diamagnetic. If it is positive but small value, then paramagnetic. If it is positive but high value, then it is ferromagnetic. Okay, so it gives us a better feeling for these materials. And yeah, here it shows for diamagnetic it is equal or smaller than 1, equal or bigger than 1 but smaller than 0. For paramagnetic, bigger than 0 but not bigger than E, which is for ferromagnetic, and it's way bigger than 1. Okay, so to explain the properties of this, we will try to introduce an external magnetic field. Okay, an external magnetic field, and see how this all materials react. According to these bases, we will know about the magnetic susceptibility, about why do they conduct magnetic field, why do they make more magnetic field, why do they attract more magnets, why are they magnets, and everything. Okay, so first, going through this, I'll explain you about diamagnetic, paramagnetic, and ferromagnetic. First, we'll talk about diamagnetic substances. Okay, so first, diamagnetic is, first they do not conduct magnetic field. These magnetic field, they go from higher magnetic field region, from higher region to lower region. That's the property. Even though they conduct magnetic field, they conduct magnets, they still go from higher region to lower region. Okay, so what I mean by this is, if this is the diamagnetic substance, and the magnetic fields are going like this, okay, going like this on this direction, okay. What you will suspect it to go through it, right? But no, this diamagnetic, it somehow makes these lines go like this. Maybe one will pass, but others will go and then will come back like this. You see over here, all the substances are, all the magnetic field lines are going like this. This is for diamagnetic substances. Whereas for para and ferromagnetic, all the lines go through the object and this go away from the object, okay. So now why this is? So here we know the field lines are repelled and therefore are reduced. But why are they reduced? Why are they reduced? So in this diamagnetic substance or diamagnetism, what happens is, in this material, it is a neutralized material, okay. What I mean by neutralized means all the atoms in this material, they have complete what do I say, they have complete octet or complete electrons. Means there is no atomic dipole. What is atomic dipole? Atomic dipole means difference in charge. Difference in charge means difference in positive and negative charge, which refers to protons and electrons. Means in this object, in this diamagnetic substance, there is no atomic dipole, there is no positive charge, there is no negative charge, they are all held together, they are neutral, okay. So when an object is neutral, okay, there's one Lenz's law, you can study that in AC current. I think in that portion there is AC current. Okay, first I'll say what is Lenz's law. Lenz's law means we know electric field can generate magnetic field, same way magnetic field can generate electric field, okay. Means because of magnetic field there can be current, okay, that's what it means, okay. Not Lenz's law, like this is the basic concept. Due to magnetic field there is current, okay. So Lenz's law states that there will be an opposing force, there will be opposing force to stop the change of current or anything, basically like your inertia, okay. Like you always resist to move, right? Same way when a diamagnetic substance or this pencil is here, okay, if I pass through the magnetic field, if the magnetic fields are going like this, okay, the magnetic fields are going like this, and we know because of magnetic field the current is produced, okay. The current is produced because the electrons will move here in bit and then they will flow, right? So when the electrons are moving, current is produced, okay. So now what this object will do, this object's atoms or electrons will try not to move, right? Because of magnetic field they're moving, right? So current is induced, so the current is produced, so this object will try to stay in rest or inertia. So this will provide opposing force which will balance the thing, and then it won't experience like everything over here, okay. Like even if you keep one normal wire, okay, if this is a normal wire, you know a normal wire will of course let the current pass through, right? But if I bring a magnet, will the current flow? No. Why? Because it's not if I bring a magnet, the current won't flow like that. Why? Because the induced or the opposing current or the opposing electrons will not let it flow. We have to connect it properly, we need to give more energy, we need to provide more potential difference, then only the current will flow, okay. So because of this Lenz's law, in diamagnetic substances the current is not flown properly, so there's no atomic dipole and the magnetic field is not properly working, okay. So basically because of Lenz's law there will be an opposing force to stop the charge of current, okay. So but this charge of current was due to magnetic field. So this will try to repel this magnetic field. Okay, so over here in this case we took that magnetic field is making the current. Okay, if we are making the current by magnetic field, can we stop the current by not having that magnetic field? Example, you're getting pushed by someone, right? What if you push that guy back? Okay, like if this is you, okay, and this is some other, this is you, this is second person, he's trying to push you, okay, but will you push him back so that he can go right, so he can go aside, right? Same way, if this is an object, this is all the lines coming, they will repel, this object will make them repel, okay, like over here. So that's the property of this. There is no atomic dipole, okay, so the electrons are tightly packed, okay. If the electrons are tightly packed, will the current flow? No. Instant they'll give opposing force, okay, instant they'll give opposing force, which will make it oppose the magnetic field, and therefore this substance won't have correct magnetic field, okay. So magnetic substances are those which have tendency to move from stronger to weaker parts of the external magnetic field. Why? Because of Lenz's law, because this is already stable. If I do magnetic field, then this material can get unstable, okay. If you're stable, then you would rather to become unstable, right? You would not become unstable, you will stay stable, because like stable is way better for you, right? So you will stay stable. When you're stable, then why does they have to go to the strong magnetic field? They'll come to the weaker magnetic field, and then they can relax easily, okay. In other words, the magnet would repel a diamagnetic substances, okay. This image shows blah blah blah. So this is how it happens, okay. So all the magnetic fields are coming, and most of them are repellent because of Lenz's law, okay. The simplest explanation for magnetism is as follows: electrons in the atom orbiting around the nucleus possess orbital angular momentum. You know there'll be electrons all over this object, right? And the electrons will move around these atoms, right? So when the electrons will move around these atoms, they will have some angular momentum, right? That angular momentum they're talking about, angular momentum. These orbiting electrons are equivalent to current carrying loop, and thus possess orbiting magnetic moment. So these are basically having current, because when the charge is moving, current is flowing, okay, basically. So in an atom, if this is an atom and this is an atom, okay, this is an atom, this is the positive charge, this is electron, this will move, right? When this is moving, electron is moving, what is movement of electron? Charge, exactly, okay. So they behave like charge, so they behave like current carrying loop, and thus possess magnetic moment, okay. So when the electron is moving, they make magnetic charge. Why? Because current produces magnetic field, exactly, okay. But for diamagnetic substances, the other one in which the magnetic moment in an atom is zero. Why is the magnetic moment in an atom zero? Because there is no difference in charge. When there is no difference in charge, they are already stable. Then why will the electron move? So the atom or this proton is tightly packing this electron, so it won't flow that much, and there will be no current, okay. So when the magnetic field is applied, those electrons having magnetic moment in the same direction slow down, and those in the opposite direction speed up, okay. This happens due to induced current, which is in Lenz's law, okay. And the magnetic in the direction to the applied force and hence repulsion, okay. So what it means is, like, you see, if this is 1, this is 2, this is 3, this is 4, okay. So if this is one object, so some atoms, the electrons will move like this direction, some electrons will go from down like this side. This is anti-clockwise, this is clockwise, same way, this is anti-clockwise, this is clockwise, okay. So when the magnetic field are moving like this, they all have same charge, right? What do they prefer? They prefer to be stable, right? So to prefer to be stable, some of them won't do anything. Like example, if because of this magnetic field the clockwise are the ones that are affected to make to have instability. Okay, so because of this the clockwise directions have instability, right? So what will this material do is the clockwise ones, it will make it less visible, like in less power, and the anti-clockwise will be in more power. Okay, so the clockwise will be in less power and the anti-clockwise will be in more power, which will repel. Okay, basically what I mean is if this is one person A, this is second person B, this is second person C. Okay, if due to A, B will, if due to A, like this guy pushes, okay, pushes, and look, they both are like friends. Okay, they both are friends, they are talking easily, no worries. Okay, they are having fun and all, but A guy is the enemy. So A guy will try to push B. Okay, wait, from this B is weak and this is strong. Okay, now they're stable, they're talking to each other. Okay, so this A guy will come and try to push B. Why? Because it's weak, right? Now they're instability, they're normally talking and all, right? So but this A guy will come and push to B. So when this A guy pushes B, he'll fall down, right? So how to prevent that? C guy will come, he will repel the guy A, so the B won't fall. Same way in electrons, in the atom this happens. Okay, you don't need to understand this concept, you just need to say because there is no atomic dipole, magnetic field is repelled by Lenz's law because of no dipole, because no atomic dipole. Therefore it goes from higher to region, therefore goes from higher to lower. That's it. Okay, you got it. What happens, like example, this guy's one electron, this guy's another electron, this guy's another electron. Okay, so he will try to push him for instability, but he'll come and he'll push him instant, so this guy won't be unstable. Okay, so this is stable, he wants to make instability, but they'll make an opposing force which will prevent this instability. That is the property what diamagnetic have, which causes no magnetic properties or like magnetism and all. And then these are some of the materials in which diamagnetism is present. The most exotic magnetic materials are superconductors. These are metals cooled to very low temperature and exhibit both conductivity and perfect diamagnetism. So they do have free electrons, but they have no atomic dipole. Okay, there is a difference, but like you don't need to know much about it because it's not much in our syllabus. So like, yeah, because sometimes that material also has that nature, like some things we cannot explain. Okay, so some properties or materials we cannot explain. Okay, so even though they have electrons, they can conduct perfectly, they do not exhibit magnetic properties. Okay, that you need to know. These are superconductors, and this phenomena of superconductors is Meissner effect. Okay, this is Meissner effect, this is special. Okay, that's why this is special. Okay, and like you don't need to know about it. Okay, so it's fine actually. And then our next material is paramagnetism or paramagnetic substances. So the difference between diamagnetic and paramagnetic is, here there was no atomic dipole, but here there is atomic dipole. This single atomic dipole will change the whole course of the magnetic properties. So what happens when there's atomic dipole? What does atomic dipole mean? Atomic dipole mean difference in charges. Means if this is one object, this is atoms, they probably have electrons. Difference in charges means what does it mean? If this is one electron I mean, like, if this is one atom, this will have positive and negative charge in huge difference. Okay, no atomic dipole means it is stable like this. Okay, like seesaw. If this is seesaw, then it will be stable, right? But what if there's more electron? Then it will be like this. Like, if this is positive, this is negative. Okay, and if negative is more, it will be like this, right? Because negative is more, right? So this difference in charges. Okay, like how in seesaw, if two persons are sitting, if one person is skinny and the other person is bulky or fat, the seesaw will have difference, right? Same way, if in an electron there's more electrons, there will be difference in the charge of an electron, right? That's atomic dipole. Okay, so that's difference in charges. So means these all atoms will have negative charge. Negative charge means there'll be free electrons, there'll be more electrons. Okay, so there'll be free electrons in random places. Okay, in random places, like random places. Some electrons are moving up, some are moving down, some are moving right, left, like some are moving up, down, right, left, upside down, anywhere. Okay, so when an magnetic field is applied, these electrons will align in the direction of the magnetic field. You see over here they were in random positions, but over here they aligned in the direction of magnetic field, right? So now when they aligned, can these lines pass through this? Yes, they can. So now, do they conduct a magnetic field? Yes. So are they magnets? Yes. So this one thing of paramagnetic changes the thing of the material, the properties of the material. Okay, so paramagnetic are those which get weakly magnetized. I mean, they have atomic dipole, but that atomic dipole makes it less conductivity, like not too much. When an external magnetic field is applied, okay, they have tendency to move from a region from weaker to stronger because they conduct. So like they can, right? If they're able to conduct magnetic field, then they will like magnetic field. If they like magnetic field, then of course they'll go to that magnetic field, right? Exactly. And they get weakly attracted to magnets. This happens why? Because the individual atoms of a magnetic material possess a permanent magnetic dipole of their own. Means that they permanently have some magnetic dipole. Magnetic dipole means magnetic means magnet, dipole means two poles difference. Okay, so they have difference of poles of north and south. On account, there is motion of atoms. Okay, when there's motion of atoms in the presence of external magnetic field which is strong enough at low temperature, the atomic dipole moment can be made to align in the point in the same direction of magnetic field. Okay, so basically when we are at high temperatures, electrons are excited, they move here and there, they move here, down, left, right, down. Okay, so if we decrease the temperature, if we lower the temperature, so now they won't move that much because now they have less kinetic energy, and we apply the magnetic field. Okay, so when we do these two things at low temperature and magnetic field, these electrons will align in one direction. Okay, this shows these field lines get concentrated inside the material. So when the magnetic field are coming like this to this object, they will go inside this and then they will start to align, and because of this align, the magnetic field lines will pass through it. You see here, they're passing through it, right? It's because of that simple reason. Okay. Okay, so these are few of the substances by which the these are some of the paramagnetic materials. Okay, this one. So now we talked about temperature, right? We just talked about temperature, right? So temperature plays a key role in the magnetization of the material or the magnetic properties. Okay, so if the temperature is more, the material will conduct less magnetic field, or it will be less magnet. Okay, so if temperature is high, the magnetic properties is low. If the temperature is low, the magnetic property is high. How do we know this? I'll give an example. Okay, like it's not truly accurate, but you can say it. Okay, if this is one material, magnetic field will go like this, and because of this, all things are aligned this way, right? What if I increase the temperature of this? When I increase, okay, when I increase it too much, will this electrons become unstable? They'll move here and there, right? Example, if you are beating one person, at some point he'll be able to be like, okay, fine, it's less painful. But when he's been beaten a lot hardly, he will start to react, right? Same way, because of this increase in temperature, these electrons will start to react. So some of the electrons will go here, some of electrons will go here. They'll have kinetic energy. So because of this kinetic energy, they will move freely. Okay, they will move freely, which will reduce the magnetic properties. Okay, so that's Curie's law. Okay, that's Curie's law. Okay, so due to Curie's law, we got this formula. Okay, this formula, and you can see, you don't need to know about it much. This C is so what is this? X is magnetic susceptibility is equal to C mu naught by T. C is Curie's constant. It is different for every object. Mu naught is the constant for permeability of magnetic substances, and T is the temperature. So here you can see that magnetic susceptibility is inversely proportional to temperature. Means if you increase the temperature, this will be reduced, and if this will be reduced, it will be less magnetic. Okay, thus for a paramagnetic material, rubber also depends upon the temperature. Okay, so for a paramagnetic material, it depends upon X and mu naught, which is the permeability, and but it also depends upon temperature. So when as the field is increasing or the temperature is lowered, when the temperature is lowered, the magnetization increases until it reaches saturation point. Okay, at which all the dipoles are perfectly aligned and no longer valid. So basically, when you increase the temperature a lot, magnetic properties will reduce. But if you decrease the temperature also a lot, if you make the substance more colder, then also this law won't work. Okay, so imagine if you freeze one thing, will the electrons move? Like, I mean, we know it is not exactly possible, but just think about it. If you are kicking a football, okay, and you freeze the football, will the football move? No, it won't. Same way, if you lower the temperature too much, it won't work, and if you higher the temperature too much, it also won't work. Okay, so that's Curie's law. And now the second last topic is ferromagnetic. Okay, ferromagnetization. So ferromagnetization, this is the next type of paramagnetization or paramagnetic substance. So ferromagnetic is the next type of paramagnetic. Okay, so in ferromagnetic, what do we know? In ferromagnetic, there's magnetic susceptibility is very, very high and positive, right? That's the difference between paramagnetic and ferromagnetic. Means there is more atomic dipole charges and there's more magnetic susceptibility, which makes it more magnetic. So why does it have more magnetic susceptibility, and why does it have more effect in magnetic dipole? Why does it have more? So in ferromagnetic, its structure of substance is quite different. So in a ferromagnetic, a substance is divided into domains. Domains means sections. Okay, so each section will represent one direction of charges. Okay, so each section will have each section will have atomic dipole. Okay, so and they'll have in one direction. So if I call this as domain A, or section A, section B, section C, section D, this will have in right side. Okay, this will have downside, this will have left side, this will have upside. Okay, this is special for ferromagnet. Okay, they somehow are arranged in this appearance that they have sections which represent one direction. Okay, there will be more directions. One can be slant right, one can be like this, one can be like this. This a lot. Okay, there's a lot. You don't need to worry about that. There's a lot. So when the magnetic field is passed through this, like this, some of the sections are already aligned, right? So when these are already aligned, it is automatically conducting, right? What was in paramagnetic? In paramagnetic, they were in this stage, right? Random, but then they aligned like this after applying the magnetic field. But over here they're already aligned. One section is already aligned, and slowly the other section will also get aligned. So here extra align, and you need to put less energy or less magnetic field, right? Because this section is already aligned, and if you put some magnetic field, this also will align, this also will align, this also will align. So because of this domain characteristics, this ferromagnetic conducts or shows more properties of magnetic field. Okay, so ferromagnetic substances are those which get strongly magnetized when placed in an external magnetic field. They have strong tendency to move from a region of weaker magnetic field to stronger magnetic field, that is, they strongly are attracted to magnet. So why is this? And first of all, it possesses a dipole moment as in paramagnetic field, but they are quite larger. However, they attract with one another in such a way that they spontaneously align themselves in a common direction, which is macroscopic volume called domain. Okay, but the property in this is, here it is randomly arranged. Over here, the dipole moment will be arranged in such a manner that it will align itself without a magnetic field itself in domains, in section. Means it will already align itself and it will be in magnetic stage already. Okay, and this explanation is by quantum mechanics. Like, we don't need to know about it. It's like too much deep into this book. Okay, and it is beyond the understanding of this textbook, like CBSE. They made it easier for us, so like, yeah, just understand it. And then this is just an example they give. Okay, so when we apply external magnetic field, the domains orient themselves in the direction of magnetic field, and simultaneously the domain oriented in the direction of B will grow in size. This existence of domains in the motion of magnetic field are not blah 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 blah. Okay, so like that simply. So what this means is, if this is 1, like this, oh wait, this is up, this is down, this is right. Now you see 2. So this is first stage, okay, where there's no magnetic field. But when the magnetic field and field lines are passed through this, it will be in this case. Bam, bam. You seen this? First this was small, but now this became big, huge, right? This is what they're seeing over here. They grow in size. The one in the direction will grow in size, means basically this will also get affected. You know, like some of the things will also get affected, like this will change into this, this will change into this, this will change into this, and basically it will grow in size. That's the thing. Okay, thus in paramagnetic materials, the field lines are highly concentrated, and in non-uniform magnetic field, the sample needs to move from towards digit to high. This is simply in some ferromagnetic materials, the magnetization persists. Such are called hard magnetic or hard ferromagnets. Means some materials, they are too much magnetizing. Okay, so even if there's no magnetic field, okay, it still will conduct magnet. Okay, so example, you're pushing one guy, okay, and when you push him, he's falling. He'll fall because of the hill, right? if you push him down of the hill, and he'll continue falling, right? Same way, in hard ferromagnetics or in hard ferromagnets, if once you put the magnetic field and if you remove it, it will still have the magnetic property and it will still conduct materials, okay? And such materials for paramagnetic are to be used in compass, because in compass we know how much we need compass. Compass cannot show it once. We need compass for a long time, so we use this hard ferromagnetics in compass. On the other hand, the ferromagnets on which the magnetization disappears on removal of external field are called soft ions. Means when there is magnetic field, they'll show where the magnetic field is, and then instantly they won't show, okay? These are called soft, or these are also called soft ferromagnetic materials, okay? These are made up of iron, copper, blah 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 blah, okay? So the ferromagnetic also depends upon temperature. Basically, the high enough temperature, a ferromagnetic becomes paramagnetic. Means basically, if you increase the temperature, they will start to go here. They'll start to have too much kinetic energy and they will move, right? So basically they'll make it from ferromagnetic to paramagnetic, and then later from paramagnetic to diamagnetic, okay? Because why? Because this domain structure disintegrates with temperature. The disappearance of magnetization with temperature is gradual, like it is slowly, but not instantly, but slowly. It is a phase transition, reminding us that the melting of solid crystals is basically like melting, okay? Like it's a slow process, not that fast. The temperature of transition from ferromagnetic to paramagnetic is called the Curie temperature, okay? So when an object becomes paramagnetic from ferromagnetic, this is called Curie temperature. At that temperature, like this boiling point, melting point, same way, Curie temperature is the temperature from which an object becomes paramagnetic from ferromagnetic, or the temperature at which a ferromagnetic becomes paramagnetic is Curie temperature, okay? And the susceptibility above is basically inversely proportional to 1 by T. And this is the small thing about Curie's temperature. You don't need to know about this. This is also out of the topic, so yeah, don't worry about this. But like, these formulas are important, so just remember it, these formulas. Okay, so now we'll be seeing about paramagnetic and electromagnetic. So substances which at room temperature retain their ferromagnetic property for long period of time are called permanent magnet. Means, what are hard ferromagnets, right? The magnets which always are highly magnetizing, those are permanent magnets, okay? And this is about theory. And then an efficient way to make a permanent magnetic, okay? So how to make a permanent magnet, how to make it is to place a ferromagnetic rod in a solenoid and pass a current through it. Means if this is a solenoid and this is a ferromagnetic rod, and the current is passed through this, because of the solenoid there will be a external magnetic field produced, right? So because of this external magnetic field, there will be magnetic field influencing the ferromagnetic, and this will cause more power for this ferromagnetic to magnetize. And if we let this current flow for a long time, it will be permanent magnet, okay? So for this to happen, the material of this ferromagnetic should have high retentivity. High retentivity means it should have high resistance to not block the current, okay? Means once the magnetic field is passed, okay, it should not resist too much. Like when the current is passed through it, this solenoid should still have the current flowing through this, even if the current is slowed. And the magnetic should be strong and high coercivity. Coercivity means this should not be able to resist the magnetic field, and this retentivity means this should not be able to resist current, okay? So that the magnetization is not erased by stray magnetic field, temperature, or motion mechanical damage. Further, material should be high permeability. Magnetic field is directly proportional to permeability, so if it is more permeability, it will conduct more magnetic field and it will be more magnetizing. Example, steel. Okay, and the thing is, and they're relating the two objects. Steel, they have smaller retentivity than soft iron, but they have high, but iron have but it this is overweight by much smaller coercivity of soft iron. So steel has steel has low retentivity but high coercivity, and soft iron has high retentivity but low coercivity. Okay, because of this steel, because what is mainly important, the property to not erase magnet, means the property to have the magnetizing power, that's more important over here. Okay, and other magnets, core of electromagnets are made up of ferromagnetic materials which have high permeability and low retentivity, such as soft iron and all. And this is theory. Okay, along with soft iron solenoid. So when we pass a soft iron, when we place a soft iron node into a solenoid and pass in a current, we increase the magnetism of the solenoid by 1000 volts. Means more the amount of solenoid turns, more the current will be there, so more magnetic field, and then it will be more affecting this soft iron. Okay, and this application also helps in AC current, which is the next chapter. And yeah, and this is all theory. So this is all part of this chapter. That's all. Thank you very much.